Hello, in this video, I will do example 6 of a related rate word problem. So in example 6, it says a conical tank vertex down is 10 feet across the top and 12 feet down, 12 feet deep. If the water is flowing into the tank, if water is flowing into the tank at a rate of 10 feet cubed per minute, find the rate of change of the depth of the water the instant if it is 8 feet deep. So find the rate of change of the depth of the water when the water at the instant if it is 8 feet deep. Okay, so think of, okay, so you have this upside down cone. So uh, yeah, you have this upside down cone and water is being poured into that upside down cone. Okay, and then yeah, you have this water is being poured into that upside down cone. And yeah, water is slowly heading up. And they tell us that this length here is 12 feet. And this length here is 10 feet. And then they tell us that if the water, so this is before water is being flowing in. So when water is flowing in this cone, the height and the diameter will no longer be 12 feet. It's going to change, right? Uh, kind of like a balloon. When you put water in a balloon, nothing stays constant. Okay, so now it says if water is flowing into the tank at a rate of 10 feet cubed per minute. So that is a volume and that is a rate, and that would be my dV dt. And since you're adding water, it's going to be positive. So you have 10 feet cubed per minute. They're asking us find the rate of change in the depth of the water. So that means we have to find. Wait, first off, what formula shall we use? Well, this is a cone and we're talking about volume. So we must know the volume of a cone, right? That would be the most appropriate formula for this problem. So the volume of a cone is 1/3 I r square times h, right? And the thing is, okay, so what is the problem with this one? We have three variables, v, r, and h. There are three different variables, right? We have three variables, and we were only given one rate, right? One rate. But shouldn't we have two rates if we have three variables? Yes, we should. So what that means is we're probably going to have to substitute one of our variables with one of our known information. So like I said before, when what we know is when you add water into a cone, everything changes. So nothing is constant. Nothing is constant. Uh, so yeah, we can't really use a substitution, but we'll try to do yeah, since everything it's not constant, we can't use substitution, so we'll have to create a proportion by the information that was given. So what do we know? Okay, so we also know that when water is poured into the cone, so when water is poured in the cone, the radius and the height will change together. right? So when water is poured into the cone, the radius and height will change together. So let's make a proportion. So radius on top and then height on the bottom. And we know we were given the height is 12 feet and the radius is 5 feet. So this would be 5 feet here and then 12 feet there. Okay. What do you think which variable must go away? Uh, I think the radius must go away. So if you kind of like cross multiply, this would be 12r equals to 5h, right? 12 times r equals to 5 times h. And if we solve for r, we would divide both sides by 12. So my radius is 5 over 12 times h. Okay, so now what we're going to do is substitute that value into our volume formula. So volume is 1/3 pi r squared times h. And I'm going to substitute that value. So that would be 1/3 pi, and then my radius is 5 over 12 h squared times by h. So this would be 5 times h. 5h squared is 25h squared. 12 squared is 144 times it by h times it by pi over 3. And when you kind of put it all together, you're going to get 25. Volume equals 25. 25 pi h cubed over 432. Okay, so now what I'm going to do is take the derivative in respect to time, and we're trying to solve for what are we trying to solve for? We have dv dt, so we need to find dh dt. Okay, that is what we're trying to find, dh dt. So let's take the derivative in respect to time. So on the left, the derivative in respect to time would be dv dt, which we have. And then the derivative of 25 pi h cubed all over 432, you would apply the power rule. So multiply 3 by 25. That would be 75, right? 3 times 25 is 75 pi h squared over 432. And then you have the dh dt. Okay. Before I get rid of 75 pi h squared over 432, maybe I could reduce. Yes, I believe it could be reduced by 5. So this would be 25 pi h squared times by dh dt over 144. And then what I would do next is solve for dh dt by multiplying all sides by the reciprocal of this. So the reciprocal of that is 144 over 25 pi h squared. Okay, so because I want to solve for dh dt, so this cancels, and then on the left, you are left with 144, 25 pi, and then my height. What is my height? My height was 8 feet. So 8 feet square times it by dv dt. dv dt is speed, which was 10 feet cubed per minute. And that gives you dh dt. So when you put it all together, 144 times 10, that's 1440 feet cubed. And then on the bottom, 25 pi times 8 cubed. Well, 8 feet squared is 64 feet squared. Times it by 25, that'll be 1600 pi. And then you have feet square per minute. And that gives you dH dt. Okay, so your final answer, 1 reduced dH dt is 9 feet over 10 pi per minute, right? 10 pi minute, because the feet cube over feet square is just feet, and then you're still left with minute. So this is your speed. This is your dH dt, which is what they want to know. Okay, that was example 7, or example 6. And what made this problem a little bit more challenging than the other one, the other cone problem, is that we kind of had to set up a proportion because none of these, the height and the radius doesn't stay constant, right? So we kind of had to set up a proportion for this one. Then we substitute it. Okay, so that is example 6.